Hi everyone. This is a video about reachability and prototyping cells inside IsaacSim. We will be going over some code that I've written about which you can use as a reference for writing your own reachability studies inside Isaac. Um, what we're looking at here is the results of one of my reachability studies where we want to pick and place things from these two palette areas. Um, Something we'll do in this video is we'll load in a different robot. We'll see how it goes. We'll see how much we can extend the range because it'd be great to be able to, put 6 boxes on each side and move things between them. And we can also add like some wacky areas that are not just on the floor. Maybe there's like something we need to pass it through, like some like, buffing or grinding or something like that. So we'll also be showing like just blocking out some basic tools inside Isaac Sim and how you can kind of really quickly build a scene that is representative of your real life cell without having to do highly detailed modeling. So first, I'll explain what we're seeing here, and then we'll go in and make all the modifications and just play around with it. So these green squares, I've sampled these two areas. We can think of this side as the input area and this side as the output area, but that's not really important. Basically, these are two areas where we want to be able to get the robot in, manipulate things, pick them up, take them around to the other side. And so what I've done is I've sampled a lot of points in here. I've told it, do 8 points along each dimension. So we got 8 along this way, 8 along this way, and 8 up high. We can, once we're pretty happy with an area and we think it's like looking good, we can go in and put a lot more points in there. It'll take longer to run, but that'll give us a really solid feeling that we can reach everywhere within that area. But yeah, we just do less points for when we're like rapidly iterating on what the areas should be. All right, so let's jump into the code and I'll explain it and we can make some changes. So over here, there's a couple files, and the main file here is this reach.py file, and we'll also go into this IK server there as well. So reach.py is a regular Isaac Sim standalone simulation app. So, we start our simulation app as per normal, then we can do our Isaac Sim imports. There's really not much that we're using here. We're, using add reference to stage because we've got a bunch of USD files that we want to add in to our simulation. We've got a world because we need a world to work with. We've got a visual cuboid. These are what we're making these little green squares with. It's a visual cuboid and not for example, a dynamic cuboid because we don't want them to interact with anything. They're purely for visualization. We've got a single articulation for controlling the robot. An X-form prim. These X-form prims are for in here, like the way that we tell this code about where these areas are is I'm not hard coding these like the coordinates of these boxes into the software here. These are actually all set up in Isaac Sim, so we can come here and we can see in our stage over here we've got infeed area, and then we can come around here. We can see that set as the corner of here. And that's really nice because that means we can rapidly prototype in Isaac Sim and just drag things around. The extents of this box, so like the height and width and length, they are hard coded in. They're easy to change, and you can get a really good idea of what they're supposed to be by manually inspecting here. But definitely an improvement could be you could set an infeed area by, like, you could create a cuboid in here, for example, and then drag that around, and that'll be a really visual cue of where your infeed area is, and then this program could read from that. Or you could have, for example, like two X forms. One could be the start, one could be the end, and then that'll define like a cube area for your infeed. And then we've got some like sci-fi rotation stuff, and I've got this library, this module called spatial utils, and this is kind of just a bunch of NumPy helper functions for working with 4x4 homogeneous matrices and composing those. Um, okay, so I think to start off with, we've got some normal boilerplate for loading in things. We've got setting our paths for our robots that we want to load in. I've got the 5 kilogram version of the Gopher here, but I've also got, we'll have a look at how this runs later. We've got the 12 kilogram, so we can easily see how things compare between the 5 and the 12 kilogram. Okay, so next we have just a bunch of loading in. We got add references to stage. So we've got our normal scene, which we'll load in. It's just called scene 2, just iterating on things there a bit for the video. And then in there, we've got a place we expect for the robot to be mounted. So we'll mount the robot to that. We'll also get the location of the robot mount. Is what we need. This is kind of what we're using the Xform prims for, because that will let us figure out where the base of the robot is with respect to the world, and that allows us to do our IK calculations, which are done with respect to the base of the robot, but our in-feed and out-feed frames are in the world frame. So we need to be able to convert between those. We figure out where our flange is. We attach our end of arm tooling to the flange. In our case here, I'll pause this. Let's just get that up a bit. So our flange is this. This is a standard flange. This is a standard end of arm tooling that we use at Workr. So we have an on robot. I think that's a VGC10 electric vacuum gripper. They're super nice and easy to use, and our camera there as well. And there's also a light. Maybe not in this exact model, but yeah, there could be a light in there too. So this is setting up all of our frames, and then the next thing we need to do is we need a helper function for generating all of these points. That's what this generate points in area is. We give it the origin, our lengths, and then the number of points we want along each side. We could also customize the amount of points for each side, but for right now, for our purposes, just having the same number of points is perfect. And then, yeah, we just get the origin and translate it by the X, Y, and Z. The frame that this is in is we assume they're all in the same frame as the origin of their space. So if you want the gripper to be, for example, facing in some wacky orientation or something, then you can put this frame here in a wacky orientation, or you can manually apply come in here and do a RZ deg or something, or su.rz deg 90, and then the end of arm tooling, the vacuum gripper will be 90 degrees from what it is currently. So we can customize everything like that. I've got some helper functions to do inverse kinematics and forwards kinematics. For right now, going through the code, I'm not going to explain how these are done, but we will go back and do them afterwards. And so what we do is we've got our two areas. We've got our in-feed area, our out-feed area. We'll generate points for them, and then we'll go and we'll solve our IK for each one of those. So we're going to do batch IK because that's a lot faster than doing individual IK for each one in a for loop. And then we'll do batch FK as well. We want to do the forward kinematics to find out, hey, this solution that came back, is it any good at all? And find out where it is in the world as well so that we can visualize it. So for each one of those, we then figure out where the end effector is from doing the solution, and we can see that comes from doing the forward kinematics. We can calculate the error. We're just calculating translational error at the moment, but you can also add orientation error. We calculate the color. If it's more than I'm blanking on the units right now. I go between millimeters and meters all the time. So it's going to be red, RGB, if the error is more than... What did I set this up to be? Well, that looks to be 10 centimeters, because we normally use millimeters internally, but IsaacSim tends to work in meters, so that would be 10 centimeters. We could even reduce that, but yeah, 10 centimeters is fine for our purposes right now. Then we're setting up some visual cuboids. One, this is the goal. This is where we were meant to go. And then the result is like, this is how close we got. So these cubes should ideally be in the exact same spot, but they're not always if you get a failed solve. And so it's very interesting to see if the solve failed, where did it end up? Because that will show you the bounds of your space. And we'll see that shortly as we start to increase the size of this area that we're solving for here. And you start seeing these interesting, like, curved artifacts, which makes sense because, we're the robot's made out of revolute joints, and so we don't expect it to have a square working area like a gantry robot might. It makes sense that it's got a round working area. And then we add them all to this list of solutions, and then here's where we actually run the simulation. We go through, if I play this again, we'll see we're looping through all of these things, and that's what this inner loop is for. That's what this inner loop is for, and then we show each solution for 10 frames, and that's how we get this visualization here, which allows us to sanity check everything that's going on. Like, for example, before when I was working on this, I was getting some wacky solves where the arm, would be like completely backwards or like upside down in a really awkward area. And so visualizing the actual solutions, not just seeing if things are green, they let you know if you're getting collisions with the environment or solve collisions or just solves that you would not want in the real world. And that allowed me to tweak some weights of the IK solver to get these nicer solves. So let's go over. Actually, before we get to IK, let's play with things a little bit. So what we can do is we can open up the base scene here. You can see we've got all of our, we've got the robot mount. It sits on the robot stool. We got the out feed, we got the in feed, and then a bunch of boxes that like sit on top of that. Let's make a new area, actually. Actually, before we get to a new area, let's see what happens when we make one of these areas a bit bigger. We don't have to manually edit the USD file to make the area bigger because, as I said, the extents of the area are set in here. So I'm saying, this is saying that the area in the X is 1.1 meters long. So that's from this side down to this side, or 0.4 meters across. So here to here, and 0.4 meters high. So that's kind of the bottom of this platform to just above the box. And let's say we wanted to put, let's say 6 boxes down. What happens if we double the width? So we can do 0.8 and 0.8 here, and we'll just make this slightly faster, and we'll put this down to like 5 solves in each dimension here, just while we're iterating. We'll run that again. All right, let's have a look at the results. Okay, yes, I see what's happened here. They didn't both extend out in the same way because of how the frames are set up. Let's just undo something there. So if we have a look at how our frames are set up, the infeed area starts extending out this direction. So if I extend it to go double the length, that would make it go from here all the way to here. So I would actually need to like move this back to double the length, and that's a little annoying. So what we'll just start doing is we'll just work with the outfeed area for now, and we'll leave that doubled, and then that should give us the result that we're looking for. In this case, we know that things we find for the outfeed area are also going to apply for the infeed area because we're working on the symmetric, like left and right side of the robot. If we were working in front of and behind the robot, things would be quite different because of how the robot limits are set up. Here we go. We'll also get faster solves because we're solving half the amount of points. So we'll get some better lighting in here. So here we go. We can start to see some structure in where we are failing IK. And here's where we can see the cubes with the goal. I'll just stop this moving so it's a little less annoying. We'll select here. So this is a failed solve. We could not solve here. And we know from how the code is that the small cubes are the goals and the big cubes are the result. And we can infer, because of how close these two are, this one on the right, this small one, is where we were aiming. And this is as close as the solver could get. And that's why this one has been marked as a failure. So that tells us we really are at the limit of this working area for this small collaborative robot. We really could not get another row of boxes. Look, maybe we could get one in the middle and we could have 4 boxes, but I think that would be pushing the working range of this robot. So what we can do is we can say, oh, what if we had a bigger robot? Would we be able to reach in this area better? So I'll shut these down. Let's change the robot we're using. So we're gonna comment out that 5 kilogram robot. We're gonna uncomment this 12 kilogram robot. We're also gonna set up the IK solver to be working with the 12 kilogram robot. We'll restart the IK server and we'll restart our simulation script. And here we go. We can see that's all green. No red at all. We could potentially push this even further. We are maybe having some issues at the front here. We'll see it when this comes back around. Regarding self-collisions right here. So it's good that we've got this extra space. Let's see how far out we can push it. Because we might want to not start off as close here. So we'll come to reach.py. I'm just blanking on where the extents were set. Here we go. Oh, no. Yeah. Let's say, could I put this all the way out to... let's double that and we'll go 0.16. Let's get some more points in there. The density is getting a little low. It'll take a bit longer to process, but that's okay. I should say, by the way, these robots that we're using, I'm getting them out of our robot library, and this is a GitHub repository full of IsaacSim USD files and URDF files that are for industrial robots and cobots. Right now, we support almost all of ABB's robots, and we will be supporting more brands of robots in the near future. We can access this here. If we go to Workrlab, github.com/workrlab/robots, it's all here. We've got a video for how to work with this and some quick start scripts. All right, we have our solution, and it seems I set it up wrong again. Okay, 0.8, 0.16. Okay, that should be 1.6. But it's nice to see that with that small area, we've got that large density, and we are getting all of those, it appeared to be. So, yeah, sometimes you can have random holes in your areas, and you think it's all green, but there might be random... We kind of had these interesting... One case we were trying to pick things off a table, and we had constrained some of our joint limits in such a way that the robot wouldn't flip, and those joint limits were just constraining enough that there was this very small area in our infeed area that could not, that the robot could not actually create solutions for. Um, and so that's why increasing the density is like super important. And also, like, these things are on grids as well, so doing random sampling inside these areas is also a very good thing. Okay, let's have a look at the results here. So we're seeing some very good structure here. This is definitely the limits of our working range. There's no way we're getting past there. And we're getting all green in here, but let's just see what these solutions look like and if we'd be happy with these. Well, they're looking quite sane. Um, Getting down all the way to the bottom, like at these peak areas, might be an issue because we don't want this part of the robot colliding with these boxes when we're picking up something all the way down there. Um, the solution here might actually be, and we can play with this, it might actually be, you know, we'll edit the USD file and we'll put some boxes in here, but I think they're going to come up to this line. Actually, yeah, they look great. But what we'll do to play with this is we'll say, what if we made this higher? Are we able to get really good solves in here as well? Um, yeah, let's have a play with that. So we'll come back to our USD file. Here we're working with, what's this? We're like box 4, 5, and 6, and we're working with the outfeed area. So let's modify that. Okay, so we got the outfeed. Let's duplicate that. We want to work in the movement tool. So we'll move that across here. And what if we were to stagger these like steps? We can bring this up. So, if we had some shelves or grandstand type things. And then we'll select 4, 5, and 6. We'll duplicate that. And then we can move these duplicated ones up here. How is that going to look? I suspect we might be able to solve all of these things, but it might be hard to reach down into it. But that's something we can play with as well. Like, we can move this whole thing down. Because again, like, we think we can reach everything over here, but we do want to avoid colliding with this as we reach down deep. Okay, we can save this, and then what we can do, we'll come back here, we'll end that. We made this roughly twice as high, so we'll make it 0.8. We'll make that area twice as high. And let's see the solutions we get. I'll check I'm still recording. Looks good. Alright. Interesting. Yeah, they're definitely in the green. Let's see how they look. Yeah, that's not looking the greatest. Because I don't know about the ability. It's kind of hard to see because there's solutions going on down here, but let's just like pause one of these. Let's get one as it comes closer. Let's get the next one. Yeah, okay, it's a little hard to see, but essentially what I'm worried about is Well, we can already tell we're going to need a longer vacuum arm to reach into these boxes. I believe because the top of this EOAT is too chunky to get all the way down to the bottom of them. And I'm worried especially about these last ones as well. Okay, we learned some interesting things there. Definitely a longer vacuum tube for sure. And that would mean, actually, you know what? No, this looks good. This looks good. Yeah, if we wanted to get super detailed with this, we could model these as open boxes and put our items in there and see exactly how it looks. But for our purposes, this is a really great start. It's looking like a feasible option for sure. Yeah, we can see that looks great. Yeah, yeah. I don't like seeing it this outstretched, but again, that is in the red area out here, which is not where we're picking. It is just starting to get a little close to, where we would be comfy here. But there's more. There's a little space for us to move this in, and again, we're not in the red zone, but it would be nice to figure out exactly where that red zone starts as well. But I don't want to move this too far forward because this will need to move backwards more. There is an option here actually of we can bring the robot up as well and see how that goes. I feel like we definitely need to move everything back just a little bit to see how it goes. Yeah. Okay, let's add a new area, and then we'll go over IK, and we'll leave the video there. I think this has given a really good overview of ways to do reachability studies inside IsaacSim. Okay, so to add a new area, we'll come back over to our scene, and what we need to do, let's just block out what we want the new area to be, and then we'll add the transforms that we need. So let's think about this new area. Let's say some kind of polishing cylinder thing. Let's just make a thing and we'll call it a cylinder tool that it needs to run a part against. That could represent a lot of different processes that we might need to do. So we'll get our cylinder in here and let's decide where we want this. Let's say it's over here. We'll scale this down, 0.1. There we go. For small parts, that seems about appropriate. And look, yeah, I think that is a good place to put it. But again, our reachability will tell us, can we reach that and what the solution looks like, so we can decide based on that. All right, we got the cylinder. Let's get a cube for it to stand on. We'll make this 0.1 and the X, 0.1 and the Y. We can see this out here. We'll bring it over, move it down. And actually, if we align this on, oh, that's not what I meant. We want to Z, and now we just want to increase the Y until we're under it. Yeah, if we're negative 1.5. I'm not actually sure which way this faces. Okay, robot's facing in the negative direction. Oh, robot's facing in the positive direction in the world, so let's put it around there. 1.5. I do actually have a robot in this world that we can activate, so to see how things look with it in here. Yeah, there we go. Robot's facing over there, so that is way too far. So we'll place this at 0.6. How does that look? That is looking very doable. And then our cylinder, we'll put that 0 on the Y, 0.6 here. Okay, that's looking great. And we'll reduce this a little bit. Yeah, let's say this is some machine down here that's spinning that thing. We'll create another. We'll create another block just to make it a bit chunkier and look more believable. So this can have less size, 0.7, and we'll make this 0.4 times 0.4. So that's a little workstation thing. And we'll see how that looks. Okay. So we'll save that. And now we need to add our transform. So we will create an X form. We'll call this, let's call it tool area. And let's find where that is. Okay. So we know that X is at 0.6. We know that the Y is roughly 0.7. 0.6. Oh, sorry, on the Z. Okay, that brings us to there, but really we want to be applying on this face here, so we can do some manual dragging now. That should be coming in here. That's looking great. And we'll drag this over here. And over here. And we want... Okay, so tip in Isaac Sim is when you're in the move tool, it shows the global frame. But if you want the local frame, you can switch to the scale tool. And then that'll show the true directions of this. So we want the Z to be facing that way. Well, I'll just put in, I know which way I want this facing. So we can put in, let's just actually start with the easy option of 90 on the Y. And then I think we actually want to do 90 on the Z as well. Oh, negative 90. Let's rotate it like this. Okay, so that one's 90 on the X. Yeah, I think that frame looks good. And then what we can do is we can set up our area in our script, the extents of it, to be from here up to here, which that looks like to be 20 centimeters. And that means we can get the workpiece in anywhere within this 20 centimeter, which will be perfect for applying it to this surface. Oh, we can actually see, base USD files have changed. We can save this, we can fetch it. Oh, no, Isaac Sim crashed. It does that sometimes. But that worked for me earlier. We could, we could edit it in here and then we could fetch it in our simulation. We get to see the updates. So let's deactivate this robot for scale because we'll be... Okay, we need to properly select the robot for scale. And we'll deactivate it because we're loading in a custom robot. At runtime, we don't want this in here. This is purely for our modeling benefits. And then, save that. And we need to know the tool area. Okay, it's called tool area. Tool area. We only want 3 cells on each thing. We'll get a little 9x9. There we go. 0.2. And actually the Z, we don't even want to be that high. We can make that 0.05. Okay. Then we need to actually find out where our tool area is. And that's what we can do here. We can copy how we do the outfit area. We can do a find and replace. Here, we've got our tool area. And, to tool area. And we'll see if we got our frames correct. Otherwise, we can rotate them by what's wrong. And actually, to make this faster, let's comment out that area, and we only care about the tool area right now. Alright, we got it the wrong way around. We're still solving it, which is hilarious. And that's actually a little big than what we want. So we can reduce this to be like 0.1, 10 centimeters. 0.1, 0.1, and I'm happy with the 0.05. Alright, let's come in here and let's flip it. We want to do... Okay, let's view this here. So we want the Z facing the other way. So honestly, it's kind of just easier to do it like this because I don't know what's up with these things, but when I type in numbers, they change like the other way than what I want sometimes. Alright, that just seems like it wants negative 90 there. Let's see what it looks. Okay. Sounds good. And I think the reason is, yeah, we've got it the opposite way to what the tool actually is because in the code, I just flip it. It makes things easier for at least the way I was laying out the in-feed and out-feed areas. And we might do a rotation around the Z, depending on what way it's facing it. All right, so we can see we've got it way too close, but we are solving it. And our tool is sideways, but that's okay. Sometimes you want your tool sideways, just based on like how you're picking things up and how it needs to be applied. And also we are in the wrong corner of things now. Okay, so let's move the whole thing out, and then let's change the corner that we're in. So our tool area, we can translate this. We want to be in the top corner. Now, that looks good. And we are actually going to make our, actually no, that's fine. Yeah, we can just move everything out. So if we select a cylinder, this cube, this, and this, and then we move everything out, let's say that much. Let's see how that looks. Alright, that is looking very promising. Still in the wrong area. Alright, not quite. Yeah, that will sort that out. No, not quite. This didn't save. Alright, what I'll do, this video is getting long. I will create another video explaining how we do the IK and FK, so the inverse kinematics and the forwards kinematics after this, and we'll wrap this up now. There we go, that is perfect. So, while I'm doing a conclusion, let's visualize everything here. I believe that is what we're after. So in this video, we went over a way of structuring your application to do reachability inside IsaacSim, given that you have inverse kinematics and forwards kinematics. That'll come in a later video. We went over visualizing your solutions for inverse kinematics. we went over loading in custom robots, setting up custom frames inside IsaacSim, and reading in the position of those frames inside your simulation. We saw how IsaacSim is very good for rapid iteration because you have this visual feedback and you can see everything inside the simulation and control it all with Python. And so you truly can just like come in here with an editor, block things out, change some values inside Python, and then see how things look. So yeah, here we go. We know we can pick things up on this shelf, we can pick things up down here, we can pick things up over here, and we can apply things to this cylindrical spinning doodad tool. Thank you for listening, everybody, and tune in for further IsaacSim and robotics tutorials.